Hello everyone, welcome to the lecture again. In the last lecture, we looked at the rotating frame of reference and the Euler equation of motion. Today, we are going to look at couple of examples of the Euler equation of motion, but before that, let us revisit the equation. So, let us say we have a rigid body and on this rigid body we can either have a fixed point or let us say the center of mass z, and capital X, capital Y and capital Z are the fixed frame. So, that means they do not rotate. So, we have capital X, Y and Z, these are the fixed frame, and we have a small x, y, z axis. So, these frame are the rotating frame with let us say an angular velocity capital omega. So, it is rotating about some axis and let us say the angular velocity is omega. So, small x, y and z, these are a rotating frame with angular velocity omega. Now, if the small x, y, z axis are the body frame, so that means that small x, y, z axis, they are attached to the body. In that case, if the body rotates, then the small x, y, z axis also rotate. So, in that case, small omega becomes the angular velocity of the rigid body, and if our x, y, z axis, they are the principal axis of inertia, in that case we have the Euler equation of motion, which is summation mx equal to I x x omega x dot minus I y y minus I z z omega y omega z, summation m y equal to I y y omega y dot minus I z z minus I x x omega z omega x, and summation m z is equal to I z z omega z dot minus I x x minus I y y omega x omega y. Here this I x x, I y y and I z z are the moment of inertia about the x, y and z axis respectively, and omega x, omega y and omega z are the component of the angular velocity along the small x, y and z axis. Now, let us look at an example, and the problem statement is following. A thin uniform plate having a mass of 0.4 kg spins with a constant angular velocity omega about its diagonal. AB. If the person holding the corner of the plate at B releases his finger, the plate will fall downwards on its side AC, determine the necessary couple moment M which it applied to the plate would prevent this from happening. So, in this question we have this uniform plate okay. This length is 300 mm, this is 150 mm, and we have the x and y axis which are attached to the body, and its center is the center of mass g. So, this is y axis and the x axis, and this plate is rotating with an angular velocity omega. This point is B and this point is A. So, because the x and y axis they are attached to the body, and x and y axis are also the principal inertia axis of this body. Therefore, we can use the Euler equation of motion, and the Euler equation of motion is summation mx equal to Ixx omega x dot minus Iyy minus Izz omega y omega z summation my equal to Iyy omega y dot minus Izz minus Ixx omega z omega x, and summation mz equal to Izz omega z dot minus Ixx minus Iyy omega x omega y. Let us call it equation number 1. Now, the first thing that we have to find out is the moment of inertia about the x, y and z axis, so that we get these values. So, Ixx, the moment of inertia about the x axis, that will be m a square divided by 12, where a is the length of this rectangle. So, that will be m by 12 and the length is 300 mm. So, 0.3 square. So, that will be 0.4 divided by 12, because mass is 0.4 multiplied by 0.3 square, and that comes out to be 3 into 10 to the power minus 3 kg meter square. Now, the moment of inertia about the y axis will be m by 12 into the length which is 0.15 square, and m is 0.4. So, therefore, this comes out to be 0.75 into 10 to the power minus 3 kg meter square. And the moment of inertia about the z axis can be found out by the perpendicular axis theorem. So, Izz will be m by 12 Ixx plus Iyy. So, 0.3 square plus 0.15 square, and that comes out to be 3.75 into 10 to the power minus 3 kg meter square. So, we have the Ixx, Iyy and Izz. Now, let us find out the values of omegas. Now, let us say this angle is theta. In that case, tan theta will be 75 mm divided by 150 mm. So, this gives you theta equal to 26.57 degree. And from here, because we have omega, we can find out its component along the x, y and z direction. So, therefore, omega x becomes omega sin 26.57 degree, omega y becomes omega cos 26.57 degree, and omega z is 0. And you can see that omega x, omega y and omega z, they are fixed values. So, therefore, omega x dot is 0, omega y dot is 0 and omega z dot is also 0. So, now let us put these values in equation number 1. So, we have omega x dot, omega y dot and omega z dot, they are equal to 0. So, therefore, the first term will not contribute, and omega z is also 0. So, omega z and omega z is 0. Therefore, summation mx is equal to 0 or mx is equal to 0. Similarly, my is also 0 and mz will be 0 minus, let us look at ixx. Ixx is 3 into 10 to the power minus 3 minus iyy. Iyy is 0.75 into 10 to the power minus 3 into omega x omega y. So, omega x is this and omega y is this. So, let us put it here, omega sin 26.57 degree into omega cos 26.57 degree, and this comes out to be minus 0.9 into 10 to the power minus 3 omega square Newton meter. Okay. So, this much amount of moment needs to be applied to prevent this plate from falling down. Now, let us look at another question statement, and it is following. The platform A is rotating about the fixed vertical axis with an angular velocity omega 2 and angular acceleration omega 2 dot. At the same time, an internal motor spins the uniform disc B about its axle which is rigidly mounted to the platform at an angular velocity omega 1 and angular acceleration omega 1 dot. Determine the components of the couple that is applied to the disc B by its axle. So, we have to find the couple that is applied to the disc B. Again, you can see here that small xyz axis, they are embedded in disc B, and small xyz axis are also the principal inertia axis. Therefore, we can use the Euler equation of motion. So, the Euler equation of motion is summation mx equal to ixx omega x dot minus iyy minus izz omega y omega z summation my equal to iyy omega y dot minus izz minus ixx omega z omega x and summation mz equal to izz omega z dot minus I x x minus I y y omega x omega y. Okay. And we can use this equation as I said, because small x y z axis they are embedded or attached in disk B, and small x y z axis are the principal axis. Okay. So, again to apply these equation, we should know what is omega x dot, what is omega y omega z and so on. So, let us find out these quantities. So, from the figure you can see that the disk A is rotating horizontally with an angular velocity omega 2, and the disk B is rotating with an angular velocity omega 1. So, from the geometry I can write down the angular velocity omega, which is a vector quantity, as omega 1 I cap plus omega 2 lambda cap, where this lambda cap is the unit vector which is perpendicular to the platform. Okay. So, it is given here that this one is lambda. So, let us take the unit vector along this direction. So, from here you can see that we already have how much is omega x, omega y and omega z. So, omega x is omega 1, omega y is 0 and omega z is omega 2. Okay. Now, we have to find out how much is omega x dot, omega y dot and omega z dot. So, from this equation let us write down omega dot. So, omega dot will be, let us differentiate this equation. So, we have omega 1 dot I plus omega 1 I dot plus omega 2 dot lambda plus omega 2 lambda dot. Let me write here again that this lambda cap is a unit vector which is perpendicular to the platform. Okay. Now, here lambda dot is not going to change, it is always along the z direction. So, lambda dot, so first of all lambda is in the direction of k and lambda dot is 0. Now, let us look at I dot. Okay. So, I dot will be, so you can use the relation V equal to omega cross r. Here r is the unit vector which is I. So, therefore, I dot will be omega cross I. Now, we already have omega, omega is omega 1 I plus omega 2 k and cross product with I. So, this will give you omega 2 j. Okay. Therefore, my omega dot will be omega 1 dot I plus omega 1 omega 2 j plus omega 2 dot k, and therefore, omega x dot will be omega 1 dot, omega y dot will be omega 1 omega 2 and omega z dot will be omega 2 dot. And also note that here the x, y and z axis they are the principal axis, and because of the symmetry the moment of inertia of this disk B about the y axis and the z axis will be the same. So, I y y and I z z will also be equal. Let us put this in equation number 1. So, we have summation m x equal to omega x dot is omega 1 dot and I x x is I x x omega 1 dot minus, now omega y is 0. So, this will be 0 and therefore, this is equal to I x omega 1 dot, and summation m y will be I y y omega y dot is omega 1 omega 2 minus I z z is let us say I z z minus I xx into omega z omega x. So, omega z is omega 2 and omega x is omega 1. Okay. And because of the fact that Iyy and Izz are equal, so therefore, this term will get cancelled with this term and we have Ixx omega 1 omega 2. Now, let us look at the moment about the z axis. So, it will be Izz omega z dot is omega 2 dot minus we have omega x omega y, but then omega y is 0. So, therefore, it will be 0. So, that is equal to Izz omega 2 dot. So, these are the component of the couple that are applied to the disk B by the axle. With this, let me stop here. See you in the next class. Thank you.